Our next talk is going to be given by Steve Furlanetto, who is a professor of physics and astronomy at UCLA. His talk is entitled Towards Robust Predictions of the Early Spin Flip Background. So Steve, whenever you're ready, take it away.
Okay, hopefully you can hear me and see me now.
Yeah.
Good morning, everybody. Thanks for getting online. Today I'm going to be following up Jack's talk by describing some of the details of the science that we hope to observe with these low-frequency arrays. So I will start with a figure that Justin showed a version of this in his talk. So this is the spectrum averaged across the entire sky of this spin-flip low-frequency radio background. So what you're looking at, the bottom axis is the observed frequency, and then the top axis is the cosmological redshift that frequency corresponds to. And so as you go from left to right across the figure, you're going from early times to late times. And we are observing this signal against the cosmic microwave background. The y-axis is in temperature units, but that's basically the intensity of the signal, but it's the intensity relative to the cosmic microwave background. So if these two things are at the same temperature, then it will show up as zero signal, and that's this horizontal red line running across the figure. And so the other curves show various model predictions of what this might look like, and those predictions depend on three things. The first is the temperature is controlled typically by the competition between collisions within the gas and scattering of the cosmic microwave background photons. It turns out that when the first stars form, those CMB photons are dominating. And that means that the temperature of the gas is equal to the temperature of the CMB, and you won't get any signal, and that's bad. So we need another effect to break that coupling. And it turns out the way you do that is by generating an ultraviolet background from the first stars. So those UV photons can scatter amongst the hydrogen atoms, and they mix the spin flip levels and make it visible again. They couple they make the gas temperature equal to the temperature of this signal, and so we need to know the gas temperature, and that's determined by the competition between adiabatic cooling due to the expanding universe after the Big Bang and radiative heating. And in the radiative part that's most important are X-rays, because they are able to travel large distances through the universe, and they have a lot of energy per photon to dump into heat. And then finally, the third question you have to ask is whether there's neutral gas in the first place. Without neutral gas, you won't have any opportunity to have this spin flip line. So the more ionizing photons you have produced in the universe, the less signal you're going to get, basically. Right, so if you go back to the figure, the structure that you're seeing is due to these effects that I just mentioned. So at very early times on the left of the figure, there is a weak absorption signal. That's before the first stars form. By the time the first stars form, which occurs at the leftmost data point here, this is a predicted data point for the DARE telescope that you'll hear about shortly, the signal is almost gone. Once those first stars form, though, they flood the universe with these UV photons, and that turns the signal back on. It appears at absorption. And then once the first X-ray sources appear, that absorption turns to emission. And finally, once the ionizing sources become predominant, the signal starts to disappear again. So the basic point is that this spin flip background is sensitive to three radiation backgrounds. This ultraviolet background that couples the transition, the X-ray background, and then the ionizing background. Now what I'm showing right now is the sky average signal. It's important to keep in mind that if you zoom in and try to make maps, then you get even more information. So these four panels show four such simulated maps. So the upper left is the, let's see if I can get the arrow working here. There we go. This one up here is when the first stars are starting to form. So the green is when there's no signal, and the blue is around those sites of the first stars where you're starting to see the gas and absorption. The bottom left panel is after the UV photons have filled the universe and the X-ray sources are starting to turn on. So the little orange blobs are around those first X-ray sources. And the upper right is when the whole universe has been heated up by the X-rays. And the lower right is when the ionizing photons are starting to become important. So that is the black blobs are where you have destroyed all of the neutral hydrogen. Right? So if we can make these maps, we can actually pinpoint where these sources are and learn a lot about the individual objects. All right, so that's the basic background. I want to now put this in the context of what's important about the first galaxies by sort of stepping you through a simple picture of how the first galaxies may have formed. Okay, and this is totally made up. It's all theory. We don't have any observations whatsoever. So these are most definitely wrong, but it'll give you a flavor for what kind of issues we worry about. Okay, so the first stars form very early on. We think they form in very small little clumps of gas that are, the cooling occurs in a very different way than stars nearby because it requires molecular hydrogen. We don't have any heavy elements, which are what is usually used to make stars in the local universe. It's relatively easy to understand how those first stars form, but once they form, things become very complicated. So the stars themselves actually probably destroy the gas clumps in which they live because they produce a lot of high-energy photons and then supernovae, and both of those can actually disrupt all of the gas in those little host gas clumps. On the other hand, they may actually help nearby clumps form stars, because if you have a clump that's about to form a star and you send a shockwave through it, you can actually trigger more star formation. So we think that maybe there are little bursts of localized star formation that occur, but once that burst ends, it's going to be a long time before the gas is able to fall back in and form new stars in that same place. At the same time, these stars are generating the radiated backgrounds that I just mentioned. The UV background, it turns out, is very important because that same UV background that turns on the spin-split background destroys the molecular hydrogen that you're using to make these kinds of stars. And so as you build up that radiated background, you're going to suppress star formation unless you can shield your source, your potential star formation site, from the metagalactic radiation field. And that basically requires a very big clump of gas. So as time goes on, the mass scale in which these stars can form is going to start to move up and up and up until eventually you reach a point where where you don't need molecular hydrogen to make the stars in the first place. And this occurs in galaxies that are sufficiently hot to begin with that they can use atomic hydrogen cooling to do that, and that corresponds to a so-called virial temperature of 10,000 Kelvin. However, even these galaxies are not able to survive to the present day because they will be evaporated when the ionizing photons fill the universe, because the ionization process also heats the gas to probably 20,000 Kelvin, and that's going to evaporate the smallest things. And so the first galaxies that could have survived to today will not have formed until step 6 after this, or will have to be sufficiently massive to survive this step 6 at least. Okay, so this is just one picture. And in this simple picture, 2 of the radiative backgrounds that are important for the spin-split background, the UV background, which I'm calling Lyman alpha photons, and then the ionizing photons come into play. But I've actually left out a lot of processes that are important, or at least plausibly important for the formation of these first galaxies. So for example, supernovae, in addition to potentially clearing out their hosts, also chemically enrich the region around them. And X-rays I left out entirely. These are probably generated by black holes. They actually promote molecular hydrogen cooling, but they also heat the universe and so affect the formation of these gas clumps in the first place. So the state of the art right now is that we've done fairly sophisticated modeling of these processes taken individually. All the processes that I'm listing on this slide here have been studied in at least a good amount of detail. The state of the art right now is trying to combine them into models that can explain multiple mechanisms at the same time. And there are a couple of significant challenges to that. So some of these processes occur on hundreds of megaparsec scales, while the stars are forming on scales smaller than 1 AU. And so you have a huge dynamic range problem if you're trying to simulate this numerically. And then the other problem is that when you have 8 different processes, each of which has order of magnitude uncertainties in how it occurs, there's just an enormous parameter space to explore. And I think that's somewhere where theory can help us interpret these future observations. So experiments like DARE observe a few data points, basically. And when you have so many parameters, there are lots of ways to sort of construct the combinations of data that you'll get. But if we could narrow down the theoretically allowed parameter space by understanding what self-consistent scenarios are actually possible, then we can ease the data analysis problem as well. All right, so I'll end there. I hope I've convinced you that the spin flip background basically measures three things, each of which is a very important relationship to high redshift galaxy formation because it studies the feedback processes that are really crucial to understanding that process. If you want to know more, I will end with an advertisement. So Avi Loeb and I recently completed this book, which describes these processes in either exquisite or excruciating detail depending on your perspective. So check that out if you want more information. Thanks very much.
Thank you, Steve. Great, great. Really enjoyed that. So let's see. I'm not seeing any questions on chat, but I have one for you. And what I'm wondering, realizing how difficult this might be, I'm wondering how much you've thought about using finite element models to take a look at some of these processes in the early universe, for instance, the interaction between supernovae and gas clouds, et cetera.
I haven't thought of that particular technique myself. Honestly, it really seems like all of a sudden people are moving from studying one process at once to trying to combine them. And there have been a couple of papers in this direction. My group is building what's called a semi-analytic model, which is a very simple way to combine all of these things that basically does each model very quickly. And so you can span the parameter space quickly. But where it misses out is in the details of each process. That is better with big computer simulations. I don't know of anybody who's working in kind of a finite element approach. Usually these things are done with in the context of big cosmological simulations. And I think Jordan will probably talk about something like that later in this session.
Yeah, it would certainly be interesting. I mean, I'm thinking about this is of course not in astrophysics, but the work that Bill Botke's team is doing on the impacts with the Mars-sized object that formed the moon, and it would be he's discovering some unexpected things by using that. So I would imagine the same may be true with this, but it's a very phenomenally difficult job, I would imagine.
Yeah, it's definitely early days. We're going to have to see where these things take us.
Yes, yes. All right. Well, thanks again. Really enjoyed your talk. Appreciate it.